you all for coming. My name is Sandra Brino, and this is FIRST Team 195. Our robotics team is part of FIRST Robotics. FIRST is an acronym standing for Inspiration and Recognition of Science and Technology. It's an organization that makes science and technology fun. So they create a varsity sport of the mind for kids that may not be sports minded, but still would like to compete too, such as, technical things like robotics and programming. So they create a game each year, allowing students to compete in a varsity sport, which in robotics. So it's really cool. So instead of getting a varsity letter in football, these guys have a varsity letter in robotics. So FIRST has 3,600 teams all over the world. They're in 24 countries. Of the 3,600 teams, our team, Team 195, is typically ranked in the top 10 of 3,600 each year. Last year we ended at number 8. So very proud of what they've accomplished. The program is expensive to run, and it's thanks to companies like Ametek, Hayden Kirk Pittman, that's your new name, right? That keep this program going for these kids. A lot of our students go back to work for our sponsors, and I believe you have Ollie working for you today, so that's very exciting. What they do. I'm going to turn this over to one of our captains, Andrew Bauer, and the kids are going to take it from there.
So hi, my name is Andrew Bauer. I'm one of the 4 captains on Team 195, and today I'm just going to explain a little bit about the game that our robot is tested. It's a robot sitting in front of you, and every year the FIRST organization comes out with a game, and we have 6 weeks to design our robot and actually build it. So this was done all in 6 weeks after the game was released. So this is our 2017 robot for the 2017 game FIRST Steamworks. And how that works is there's 3 different tasks in the game. One of the tasks is you have to shoot these wiffle ball looking things into this tower over here, which are located on these sides of the field. So this is a schematic of the field here. Then the next task is taking these yellow gear things and placing them on these little pegs around the field. And then the third task would be climbing a rope. So our 154-pound robot does climb a rope in under 4 seconds. Yeah, it's pretty crazy.
So hi guys, I'm Jake. I'm just going to talk to you guys basically about our general design of the robot. So starting from the drive, we have a 6-wheel, 2-speed drive. So you can see here, it can move in low speed, a maximum speed of 11 feet per second, and then high speed 6 feet. So that provides us advantages because we have high agility when we need it. It's with speed, so we can have fast cycle times, but also precision and pushing power. So if we get into a pushing match with one of our competitors, we have a lot of pushing power. And then moving from there, we have a nice intake for the balls that you see. So when we're going around, our intake will come out, and then as Chris drives around, he'll suck up balls. So our intake was, in my opinion, one of the best in the world because we had a bumper wide intake. So no matter where we were going, if a ball hit the front side of our robot, it was in our robot. And we can actually hold 80 balls, which is like one of the most that a lot of teams can hold. And from there, you see we have our turret has 500 degrees of freedom, so it can move from here and do a complete rotation around. And the key behind that was we didn't want to have a dead spot, so in the rotation. So if we're getting pushed around by one of the opposing alliance members, and we're getting turned, we wanted to be able to be locked onto the target no matter the orientation of our robot, so that we can shoot and score no matter what's happening. So if you want to show them shooting. So our turret locks onto the target with vision, which Chris will explain later, but we can actually shoot 8 balls a second with about 90 to 95% accuracy, which is pretty good. So during the first 15 seconds of the game period, it's called the autonomous, and that's pre-programmed controls. So what we did was, one thing that we were really well known for was our 40-point auto for our hopper autonomous. So what we would do is we would go to one of the containers that stores balls, and we'd shoot and hit an important threshold for shooting balls in autonomous, which would give us the entire time in the driver control. So off the back of the robot, we have a gear pickup, so we can come in off the floor, and you see. So that's kind of, we call it a hybrid roller prong intake. So the roller, you can see, so if you drop it, So that will spin and suck in the gears, and then the prongs will come in, lock and grab it. So once it's got a hold of it, it's really tough to like let it go. So that's really good. So if we're ever getting like pounded again, the gear won't fall out.
Why'd you make it so small?
Because we wanted to make as much room for the hopper as possible. That whole assembly is this big. It's very, very complex. It took a lot of iterations to come up with that well of a design. And then for our placement, we have a pressure pad. So when the spring hits a Lexan plate, it'll trigger 2 limit switches that will then run a program to deploy the gear completely autonomously. So if you want to show them that, watch the game. So he's going to drive up and he's going to say, all right, I'm ready to place the gear. So once he hits the peg, we have really low battery right now, but normally what would happen is, I'm going to do it right here. So what's going to happen is this plunger right here is going to push out, and that's what throws the gear onto the complete back of the peg. So everything together works to throw the gear on the back of the peg, because what happened in the game was there was actually a person in an airship who had to pull up the gears, and if they weren't on the complete back of the peg, gears would often fall off, which was not good. And then moving from there, we have a climber, so if you want to dump the balls in. So our climber was designed into our intake assembly. So at the end of the match, when we're done shooting balls and ready to go climb, we deploy our climber so it flops down. And this we have metal Velcro, so that would lock onto our rope, and then we'd start to spin up and climb the rope. So the benefits of having this assembly here is that as it wraps around, it gets 1 to like 3 wraps, and then it'll start to pick up the robot. So that ensures us that we'll climb every time as long as we get the rope. And we can climb in about like 3 seconds once we have a hold of the rope.
So programming-wise on the robot, there are 2 computers that we have. One being this gray box right here, the other being the green circuit board beneath it. This one is called the Robo Rio. It's the computer we're given to use, and it's how we control the robot and everything's run. And then the computer beneath it is what we use to process our vision, which is through this camera here. So that's probably the most interesting part of the program. It's like the robot can see the target with this camera between these lights and align itself and keep itself aligned. So the green lights shine at the reflective tape on the target, and then it uses algorithms to determine whether the 2 rectangles are about half the size of each other, and other parameters, so that it knows where the target is, and it filters out, like say, the lights behind it, and it's able to lock on within about a degree of deviation during the entire match, so that we can shoot from anywhere on the field. We use last year we used LabVIEW, which I know you guys have used in the past, and this year we moved to C++ for more fine control over.
As you can tell, this was a very complex game this year. We had 2 different game pieces, plus we had to climb a free hanging rope at the end of the match. So going along with that complex game, like Jake explained, we had a very complex design. One of the hardest things to design on the electrical sub-team was this full force spring here, which allows all of that degree of rotation on our turret. And in addition to that, we only have 6 weeks to build this complex robot, and electrical got 2 days of that. So at the very end of the season, you can see all of the electrical on the robot, and we also do all of the pneumatics, which is the air pressure. So we have all of our motor controllers, our solenoids, everything underneath this giant plastic hopper. So if you have any questions, that's all right here. But that's basically what it looks like. So we had 2 days to figure out how to fit everything into that space under this hopper.
So what are the dates? What date do you begin?
January 6th. So this year will be January 6th, and I think the
February 20th.
completion date is February, I think 19th or 20th.
And does all of the design occur at the facility?
Yes. Yeah. Jake, you want to talk a little bit about how you come about the design and the game?
So when we're given the game, when they release it, so it's like a live broadcast which first releases the game, we then go through and break down like the entire rule book. So we have a whole rule sub team that goes in and tears it apart so we can know what we can and cannot do, so we can make the most efficient strategy to complete the game and play it very well. And then from there we go into like a really intense prototyping season. So everything that you see in the robot was prototyped out of wood, Lexan, metal, pretty much anything we can get our hands on to make it as quickly and as kind of accurately as possible, because we want to resemble it as clearly as we can to completely visualize it. And then from there we go into our design season, which is CADing. So we're switching over to SolidWorks this year, but we used Autodesk Inventor last year. And everything you see there was designed except for the hopper. So all this, we do all this intense CADing so that, because we get a lot of out-of-house machining, like water jetting, stuff like that, so we need to give them all the files that they need to cut our parts. And then from there, we go into the manufacturing processes, which are machining all of our parts and stuff like that, and then the electrical. And then programming gets the robot, and they get the rest of the time, even after bag and tag, because at the 6th week, we bag up our competition robot, but because we built 2, they're supposed to be identicals. Most of the time, they are. Our programming team can make their program for the programming bot, and then it should theoretically transfer and be identical for the competition. And that's basically how our
So
season.
the physical location where these activities all occur, is it Sullyton High School? Is it the practice rink down in
So-
Plantsville?
The majority of it, minus the manufacturing parts, occur at Mohawk Northeast, which is our practice facility.
Yep.
We have kind of a mini shop set up there now, but the majority of our manufacturing processes occur at Tiger Enterprises, and that's he lands over there. He donates his machine shop to us, so we can go in and use all of his mills and lathes and stuff like that. And then pretty much the assembly gets done half and half at Mohawk and Tiger, and then the rest of the season we spend at Mohawk when we practice.
The very early time, we actually have a building that was donated by the Fergola family right on West Street in Southington. So we do a lot of our early stuff there, so we can do breakout sessions and brainstorming and the rules. So very early on, we're in that facility, and that's where we just have our weekly meetings and do housekeeping. But it's not large enough to do everything, so we actually have a couple of facilities.
Would anybody like to explain game strategy and scouting?
So each match we have a set of 7 or 8 people in the stands, each scouting a different robot on the field. And we compile all that information to a scouting system, and then whatever robot is the best statistics-wise and through match videos, we will use that information to pick during alliance selection later in the competition.
Well, for playing the matches, you're on alliances of 3. There's 2 alliances of 3 on each side of the field. And really, before we go out onto the field, we look at who we're up against and who we're playing with to assign how we're going to beat those robots. So the matches are different every time. Like, we do the same kind of format where we go for our autonomous mode and score all the balls and then try to get the most points possible. But when you break down the match, it comes down to more than just scoring the most points possible. It's how you're going to stop your opponent, whoever's playing against you, and how you're going to win. So we'll assign different robots to different tasks that they're good at to really maximize our potential on the field and stuff like that.
And that's all done through a database of...
Yeah, so like we said before, we have the scouting system where we have it electronically on tablets, and the students will sit up in the stands and just punch in all the numbers. Basically, how many balls this robot scored, did this robot climb, did this robot do this many gears, and then from that we'll determine if the robot's reliable. And when it comes to the elimination rounds, we'll see which one will complement us best and pick them so that we can have the best chance at winning.
Behind that is you can build the best robot in the world, but if you don't have the information out there on how to win the match, you're not going to win. It's the same thing in sports. So you can have the best football team in the world, but if you know you're playing an opponent that can, let's say football per se, and they stop the running game, but you're the best running game out there, you got to figure out how else are you going to score that particular game, or you're going to lose. And that's what we do every single match, which helps us propel forward every year. So
Not every team builds a robot as complex as this. So there are a lot of rookie teams out there that, the robot they put on the field is built out of wood and PVC, and they've done the best they can, and it may not have all the functions that this robot. There's some robots that all they do is play defense. They don't even handle the game pieces because they weren't able to figure out how to do that. So you have to figure out, if you're alliance with them and they're on your team, how can we use that robot to our best advantage as a team, even though it can't do everything that the other 2 robots can do. So it gets into some very interesting strategies sometimes.
I think I'd like to open it up to questions. Ask the students questions, anything you have about the program, the robot, the game.
How many people do you have scouting in the
We have a good 6 people.
Wow.
Per robot.
6 per match, but
There's more, though,
The
because,
scouting
like-
group's about 20 some odd students.
We've done some very detailed scouting too. We even have, so we have scouts watching the robots. Then we have scouts that are verifying the information that those scouts are putting in. And we have scouts that even scout the 4 referees to see what they're calling, so that we can understand how that, because you know, every game's different. Some games, even football games, right? The refs kind of call it hard or call it easy. Well, we want to know what's going on with the refs, so we scout pretty deep.
We also have scouting as far as circumstance-wise, like if there's a robot that's a big scorer on the other side, where is he the most accurate? Because usually there's a spot that a robot is the most accurate, and then we put a defense robot to keep him out of that spot. So
Do you
that
guys ever use some of that legacy data from years before, or does it change so much that it's not
it's basically, you can assume that, you know, legacy data, they're going to be a good robot, but you have to, every year you have to hone in on what that robot is doing, because it's a robot built in 6 weeks, and sometimes you hit the mark and sometimes you don't. And if you don't, can you recover through the rest of that season? And one particular season for us was 2015, where our first competition we went out, we really didn't hit the mark on the robot, where our robot really...
Our robot caught on fire on the
Yeah,
field.
it kind of failed. But
Like,
we went back to the shop. We had a big 6-hour meeting after that particular meeting, and we made design changes. We can change up to 30 pounds between competitions, and we made 30 pounds of changes in that 2 weeks for our next competition, to the point where we won that match and became again a top 10 robot in the world by the end of the season.
Were you asking, are we using data from other years, like there's ball pickups, there's
You develop a database over time.
Right.
How useful is that old data?
vary?
Yeah.
I mean, we use some concepts on this robot from years before with another ball
Design
robot
ideas,
for
yeah.
floor pickup. We've used the shooter, there's a whole bunch of different shooters. Not only that, but every other team's, there's a history of everybody's robots online. And all that data is made available to all the students everywhere. That's,
You guys share all of the data you collect?
anything we've got, it's,
Oh, that's awesome.
it's,
Basically open source for all the teams at
Yeah.
the end
oh
of the
yeah.
year.
Yep.
Oh, that's
Code that you guys
Even like
develop,
programming.
it's shared at the end of the season with everybody?
Yeah, we put it there. It's on a form.
It actually has to be required to be shared if you want to reuse it in the next season,
Okay.
so that other teams can learn from what you do.
First
Are
is
other
a,
teams actually using your code?
Yes.
Can't tell you that.
You
don't know? I know that we look at other teams' code to see what we can do better.
I know that the Israeli team used our design. They asked for our shooting design, and they redesigned their robot for a postseason event using our CAD design. We sent that off to them for.
That's great.
So there's also, besides the robotics and the competition and the design, there's also community relations, right? There's kind of an interesting component there.
Yeah, we didn't
Yeah,
really
we've-
explain that. Who wants to explain?
We've got some great relationships with teams from other countries. We mentored a rookie team in Turkey last year. That was fun. Israel, we helped out Israel. I don't know, who else did we?
I thought there was like, there's something in the newspaper about, I think it was from Afghanistan,
I
a
think
women's team.
Oh,
That was
yes.
an Afghan team
Yes.
down in Washington. We
A
weren't
different-
part of that.
It was a
but-
different robotics program, but one of
Yeah.
our alumni was helping them. So.
Okay,
Yeah.
don't worry about that.
The other thing we do, that we build a whole wooden replica of the field, so that field you saw that was posted up there, it's 27 feet by 54 feet. It's a rather large field, but we have a wooden replica of that field so that we can practice every day. We invite all teams in Connecticut to come and practice with us, so that it gives them the experience to actually practice on a full field. There's not too many teams. In New England, there's probably only about 3 teams that make a full field. So it's, you know, when we did it our first year, we saw how much of an advantage it was to have, and we said that we have to open this up. And there's been quite a few teams. Last year, we had, I think, 16 teams come and practice at our facility.
It's great too, because everybody's improving everybody else's robot too. So you're building good relationships going into the competitions. FIRST really emphasizes something called cooperation. So although they have a competition, they really want the competitors to cooperate together to advance learning, which is really the ultimate goal. So we do share our scouting data, we do share our design, we do share our code. We've written code just before a team is going out on the field. We've helped them fix their code, and that's all in the spirit of, you know, gracious professionalism and cooperation. So that's really what it's about. Even though it may like take away your competitive advantage, that's okay.
You have a video this year too?
We have lots of video, thanks to this nice woman right here.
Because, I mean, there's also a community relations video
Yes.
you judged on too?
Yes, we have a whole chairman's team. In fact, Batul is one of our chairman's presenters, and so she'll be presenting to the judges this year. So the team isn't all about robots. They do a lot of outreach to the community, particularly veterans. Batul, would you like to talk a little bit about that? A little bit about some of the things that are in the essay that we do?
Every year for chairmans, we write an essay, and that is filled with all of the outreach that our team does, from the youth in our community to the veterans to our fellow teammates. For the youth in our town, we are trying to put an FLL team one level below FRC, the competition that we do in every elementary and middle school that we can, so that every school has an opportunity to start robotics at an early age. And we mentor those teams that exist so far in our town. And for veterans, we put a big emphasis on our veterans. We do appreciation dinners with them. We co-work with the Elks Club in our town to make a great appreciations dinner for them. Last year we joined the Hartford Parade in order to honor them. So we do a lot for the veterans. We visited the Tomb of the Unknown Soldier in Washington a couple of years ago, so we value that very greatly. And that's just some of the stuff that we did for our veterans. And as we've listed before, for our teammates, we've opened fields, we've shared data. So our outreach, we really value our outreach, and yeah.
To us, you come to our field, we're exposed. You know, it doesn't matter to us. We're basically, you know, what we're looking for is we're looking to build a robot that can compete at the world level. I mean, that's what our goal is every year, that we can play the game to its fullest, score, you know, try to score the most you can, so that way we can compete against the NASA teams, the Jet Propulsion Lab teams, the GM motor teams, and we've done really well at competing with them. And when they come to our pit and look at our robot, and they start looking at, okay, who's your big sponsor here? We don't have a big giant, sponsor like a NASA or anything like that, where it's just a great group of people together that we really are good at problem solving.
Like this, and that make it happen.
Yeah. The elements of competition, shooting, there's climbing, obstacles of various sorts. So you probably have an idea of what are the major things you're going to have to do. So in the last 5 years, were there any really major surprises about some task that you thought was really
Everything.
very difficult?
Yes.
Everything.
Everything.
Surprises every year.
There are, and I gotta, we've done some programming miracles in the last 2 or 3 years, which I think has really put us to the top, because the programming team really works hard to
That guy, right?
to really get the most points we can, especially in our autonomous period. And autonomous is basically 15 seconds that you do not control the robot. That robot has probably 20 sensors on it, on the motors, between the motion camera. So that robot will pretty much move by itself for 15 minutes. It'll go to the hopper, get the 60 balls all by itself, and it will find the target and shoot at the target all in 15 seconds.
One of our biggest surprises, I think, to get to your question about the last 5 years, one of our biggest surprises was the fact this year, actually, how few teams even made a robot that could do balls. There were competitions we went to that all they did was the gears, because the game was designed this year to grant more points to gears. However, you max out. Once you've hung 13 gears or whatever it was, you're done.
Even if you were turning.
So the only thing that can advance you beyond that score is balls. But a lot of teams just said, hey, let's just go for the best amount of points. And that's okay at the local level, but as you start to rise at the regional level and the world level, having an efficient ball mechanism became critical to winning.
Yeah.
That was, I would say that was a big
A
surprise.
gear is worth roughly 20 points this year, and with a bonus at the end. A ball was only worth a third of a point. So it basically made robots say, well, it is a difficult thing to do, to be able to, number one, pick them up off the floor, number two, have a shooter that is somewhat consistent, because some of our prototypes, they were shooting a ball here, you need somewhat of consistency. The ball itself has inconsistencies, but if you can get, in that 80-90 percentile accuracy, now the third of a point starts to add up quick. And if you have partners now that can do the easier task of the game, which is putting up the gears, you can concentrate on putting up the balls and assist them in putting up gears so that you can reach your 13 max. But you can now get above what the maximum score you can get with the gears.
Every year is a surprise because every year it's an entirely new game. This year you see we have these wiffle balls and gears we had to place. Last year we had to climb a horizontal bar and we had to shoot a 10-inch gator skin ball. The year before that we were stacking totes. Every year it's entirely different, so it's hard to guess what's going to come. People have tried to hack it every year and figure out what the game is early. It's never happened.
I wonder about that too.
Best game piece ever was Frisbees. That was the most fun game piece.
So effectively, at the beginning of the year, this is all going to get wiped clean, and you're going to start fresh with a new. You don't know the balls, you don't know anything.
You don't know anything.
So you guys essentially you've got a foundation you work off of.
Nope, we start clean, we
Completely.
open up the computer and they start building it in CAD, so it's
Like,
a whole new design.
like Jake said, when the game is announced, so this year the game's gonna get announced in about a month, January 6th. So the first thing when the game gets announced is we don't even talk about robot. We don't talk about sensors, we don't talk about how we're doing it. The first thing we talk about is how do we wanna play the game? How do we wanna score? Do we wanna score balls? Do we wanna score gears? Do we wanna climb? And that's all we really talk about to come up with a consensus for the team of this is how we want to play the game. And once we decide that we're going to play the game, so this year what came out in that strategy session was we wanted to shoot 40 balls in the first 15 seconds. That was our initial strategy thing that we wanted to do. We wanted to be able to put up gears, that was our second thing, and we wanted to climb. So that was our three initiatives that we came out. So basically we're doing everything. But the number one priority was, the hardest part was shooting 40 balls in autonomous in 15 seconds, which is now you start doing the math to do all the movements to get the balls and to shoot them in, you need that roughly 8 per second to go in, or to shoot 8 per second and having a certain amount of accuracy to get that 40. And that first 15 seconds, the ball's worth 1 point. So that's why that was a biggie, all right? So after that, they're worth a third. So all we have to do is get 40 balls, but you only have
What's
5.
the 40? What's that number derived from?
so
That's the max?
It's a threshold.
Oh,
It gave us a rank, what's called a ranking point. So once you get 40 points in that stack there, you get a ranking point. So in autonomous, all you need is 40 balls. If you don't get an autonomous, you need 120 to get it in teleop, which now becomes much harder. So
How long is that round?
it's 2 minutes and 15 seconds. But once we do that, then we decide and start talking, okay, how are we gonna shoot the balls? Catapult, our wheel design, spring design, whatever. Then we decide to make, okay, let's try making these 3 or 4 different prototypes over the next following week. And the kids all work at making prototypes and find out which one is the fastest and most accurate. And we came up with this as being the most accurate. There's flywheels, has flywheels on the side. Because when you're shooting balls so fast, the motor speed goes down.
Yeah.
So you need the controllers to keep the motor speed at a constant speed, along with the flywheels to keep it up at that speed. And then you talk about the drivetrain. Last year we had tank drive, which is a very different drive from this year's drive. So depending on what the field is, we decide on what kind of drivetrain we want. We've done all different kinds of drivetrains. So we have all of them basically in our book of year to year. We can just decide, okay, we're going to do tank this year, we're going to do swerve drive this year. And then it goes about how you're going to get the balls into the shooter and how you're going to gather the balls. So they try different prototypes on how to take the balls in, through the bumper, over the bumper. There's all different ways to get the balls in. And you find out which one is going to work best with your design. So,
When's your onboard power?
So we just have one large. Want to grab a battery?
Everybody has to have the same thing.
That's all regulated by FIRST.
Yeah, that's one of the limiting factors, because if we have a lot of stuff going on one time, like this year we killed a battery. By the end of every match, it was completely, like we almost had,
If that was open.
we almost had trouble climbing
Max out of
sometimes.
every output.
Each, so you have,
Per match, so the
Yeah.
2 minutes and 15 seconds.
15 seconds you're draining that battery?
and then
Correct.
per competition.
There's 14 motors on that robot.
Yeah, 14, okay.
So like you see here, like when he drives right now, you see I was like juddering. That's because our battery's dead right now. That's when we go below like 6 volts, and that's not good.
Yeah.
And that, which has happened in some matches. That we do what we can. We have to adapt. That's the other tricky part about the game is it's a lot of like you go in with a solid strategy and everything, but it's all what goes on during the field, like during the match. So you have to just get in there, adapt to like current situations, what's going on, and like it's all driver experience. Like they just have to know what to do at what times, like in certain scenarios and whatnot.
So yeah, that brings up a point. So if it's shooting balls and it's off by the same angle all the time, and somebody has to go in there and fix a determinate error,
Exactly, yeah.
you fix it, right?
Yeah, they can go manual if they need
So
to.
we try to automate as much as we can for the majority of these things, just to make it less stress on the drivers, so we can do as much things without thinking. But if something were to go wrong, we have full menu control on everything on the robot. So that's why you see we have this huge button box here. So a lot of the stuff is on this joystick and his joystick. But if those automated systems end up stop working, we can go full manual with this button box.
You guys are all welcome to our facility.
Yeah, come visit.
Yeah,
Love to have
after
you.
January 6th, we meet at our Canal Street. I think it's 179 Canal Street, which is literally, I think, 3 miles from here, Jeff.
It
3,
is, like
4.
down the hill.
Yeah.
Yep.
And
Good plans for it.
we're there.
Yeah, down the pool.
We will be there every single day from January 7th on. From 6:30.
May. We'll be there till May.
From
so.
6:30 on, all the way through the end of April.
The kids are in the shop every night, 6:30 till 11-ish.
One of the advantages
Sometimes much later, depending on if there's
we
school.
we build we talked about the practice robot. So that chassis right there is our practice robot with all the top taken off. We just brought that in so you can kind of see what's going on in the guts of the robot. But that robot was identical to that one. And that's what we practice with, because you're not allowed to practice with the competition robot. It actually gets put in a bag and sealed. So you can only take that seal out at competitions. So we're practicing with this every night. It's getting a ton of wear and tear on it, and it keeps breaking down. And the students learn how to fix it. And somebody was asking me about what happens if your robot breaks at a competition in a match. Well, we have an entire pit. We basically have enough. We have everything to replace everything on that robot in our pit. And
We basically have
we make big hammers too.
Zip ties
So-
and duct tape.
So between matches, depending on your schedule, sometimes you have 20 minutes between matches. Sometimes you might have close to an hour between matches. So you hope that those big repairs are at the hour marks, but it's happened before where we've had 20 minutes and we've had some major problems. But the crew has fixed the practice robot so many times that they'll be coming off the match and they'll be calling us and saying, all right, this just happened just like at the practice field. Start getting this, and this already in the pit. And the pit will all be getting that stuff ready, so when the robot comes in, they're taking it apart, whipping things around, and getting it together for our next match again so that we can play hopefully at 100% at the next match. If we don't play at 100%, we go with what we got and change our strategy accordingly.
And so that brings up a point, so anybody who goes to these competitions, they're pretty impressive, like they have in Hartford a couple
Yes.
times, yeah, and so they allow people to kind of walk around, and if you go to them, just remember to take your safety glasses and your side shields, otherwise they won't let you in the pit area.
They actually have ones that let you borrow.
Yeah, they'll let you
Oh,
borrow
really?
them.
Okay, yeah, yeah.
They're
Okay, good.
lousy, bring your own.
Yeah, but I'm saying, it's really, I mean, there's a lot of stuff going on in the pit area, so.
Yeah, there's everything's going on.
Yeah, there's been
Chaotic.
competitions where we've been really busy the entire time, and then there's competitions where the pit is sleeping.
Yeah, we did that.
We had a robot completely apart at a couple of them.
Yep.
Yeah.
Completely apart.
2016 at World Championships, we actually had to change both of our treads. So that basically involved taking half the robot apart, which was not that fun, but we got it done.
I was thinking about the Frisbee year.
The Frisbee year,
You completely
even
disassembled the robot, didn't you?
the
at
stacking
World
year.
Championship?
Now, the stacking year we
The
did too, that
stacking
was in New
Yeah,
York.
we spent the whole practice day redoing that robot.
And going on a diet, we were 8 pounds overweight.
Yeah, I was saying, somebody was asking me about the weight before. If you look on this robot, there's a lot of holes in there. The maximum the robot can weigh without the bumpers and the battery is 120 pounds. And if you are 120.01, they make you take weight off. It has to be 120 or below.
Because
So-
everybody, like, they have an inspection list, so you have to go through, it's like a multi-page thing. They have to go through everything on that robot, make sure you're complete to all the regulations, you're using all the correct motors and whatnot. They try to, like, as fair as possible,
Pneumatics,
so
wiring,
everything
Yeah.
has to be the same throughout every team, like, based on what they use and stuff. And then through that, you have to go through, and if you don't pass inspection, you can't play the game.
Inspection takes approximately 2 to 3 hours per competition for a robot.
So what grade levels? Is it just guys start like 9th grade and work all the way?
We're 9 to 12.
To 12.
There's different programs at every age, though. First has programs for little kids in elementary school. They have First Lego League, First Tech Challenge. They're all different games, and they're geared towards younger students. So there's games for elementary students, middle school students, and then high school students. We're a high school team. So our game is more difficult and much bigger, but there are smaller games for younger students.
For us to do this, you really need all 4 years there, because the underclassmen right now are soaking in all they can from the upperclassmen here. They're teaching them along. They've already, this fall, have already been competing in what's called FIRST Robotics. It's a small robot, 18 by 18. And that program is mostly about the upperclassmen mentoring the underclassmen and getting them to teach what they have learned, and for the underclassmen to start seeing how how these different components work and how to piece them together. So it's a mentoring program from bottom to top, from underclassmen to upperclassmen to professionals.
Good.
Yeah.